Check it out, guys. Look at this. I got this piece of wood perfectly balanced, right, on our 2x4 right here. Perfectly balanced, so it can hold both sides of the books. Both sides are weighted down by these books, but it's perfectly balanced. Now, what happens if I put these other two books on this side? What's going to happen? Yeah, you're right. It's going to fall over. It's going to be unbalanced. All right? Let's think of a way that we can balance these books. What if, I know if I take two books off, it'll balance out again. All right? And some of you might be saying, I'll just put the books in the middle. And if I did that, well, you'd be right as well. Can't argue with that. But what's a way that I can put 4 books on this side and only have 2 books on this side? Can we think of a way to do that? Good idea. Let me try that. Let me try to move these books halfway inside. Now, let's see. Let's find the part right there where it balances. Wow, look at that. Yep, that looks pretty balanced. The only reason it's shaking is because of the fulcrum it's sitting on. Let's stop that. All right. That's pretty good. Look at that, that's pretty balanced. How about I get a meter stick and let's measure out the center to the center over here and over there. Let's see. Okay, from the center of the book to the center of the fulcrum looks to be about 53 centimeters. All right, so that's 1 meter. Now, if I go to the center, right there, another 6 centimeters. So it's 53 centimeters from the center of this to the center of this book, and it's 106 centimeters from the center of the book to the center of the fulcrum. Why is it exactly half if these books are exactly double? All right. What are we actually seeing here? What's the simple formula that we're actually seeing right here? Think about it. What is the weight of these books versus the weight of these books? That's right. These books are doubled compared to these books. And what are we talking about from distance from here to here versus here to here? You're exactly right. There's a force acting down on these books, but it's acting from a different distance away. So if these books are exactly doubled the weight, but exactly halved the distance, and these books are exactly half the weight, but double the distance, what are we actually seeing here? We're seeing the same amount of what? The same amount of work. That's exactly right. This lever is balanced because the same amount of work is being done by the books on this side as is being done by the books on this side. And that's how levers work. This is a first class, or a class 1 lever. So it's called a class 1 lever. And what it does is it acts the same way as a pulley. It redirects your force. So let me take these off for a second here. Let's see. If I want to lift those books up, I'm going to press down on this side. And when I do that, I have to press down with the same amount of force that it takes to lift those books up. The same amount of weight, because I'm pressing down the same distance. So what happens if I give myself a longer lever and a shorter fulcrum? Well, let's see. Let's put these back on. All right. I mean, already you can tell that the wood itself is heavy enough to lift these up. So if I want to press down on it, it almost takes no force whatsoever. So look at that. The distance that the object is from the fulcrum is relative to how much force is needed to press down. And if I really push it out far, right, it's going to take a lot of force, a lot of extra force to lift those up. I know it's out of frame, but just trust me. Let's look at another example. Let's lift up a desk using the lever. All right. Now, lifting up a desk on its own is very difficult. These things are pretty heavy. Let's see. Yeah. It's got some weight to it. But let's check it out. Let's use our lever. So I'm going to use the edge of this table as the fulcrum. I'm going to attach it right there. And I'm going to go check to see, make sure I'm in frame. All right, so now that I'm in frame, I'm going to go to show you guys this example. So earlier it took, my whole hand and a lot of force to lift up the desk. Let's see what happens now. Well, that's much easier. I can do it with one finger. Oh, wow. That's intense. Let's check this out. Let's measure the force needed to pull that desk up. All right, so again, here's our lever. I have this spring scale right here that measures objects in grams. So let's see, as we pull down, let's see how much it takes. Am I up in the air, Mr. Perkins?
Yep.
All right, we're looking at about 3,500. So 3.5 kilograms. It takes 3.5 kilograms on this side of the lever to lift up that side of the desk. Let's measure how heavy the desk is using that information. So to figure this out, we're going to need to find our mechanical advantage. So Mr. Perkins and I are going to measure from the fulcrum to the very edge of this side, to the very end of the lever where we were pulling down from.
So we got 1.
So 1 meter.
2 meters.
2 meters.
And 7 centimeters.
2 meters and 7 centimeters, so 207. And now we're going to measure from the fulcrum
To the desk.
to our desk.
Looks like it is about 31.
So 31 centimeters. So let's write that down. So we had 207 centimeters in our effort arm and 31 centimeters in our resistance. Let me write that. Effort and resistance. So what's our mechanical advantage? Well, we're just going to divide by the number right there. Let's divide by each other. So to find our mechanical advantage, we use this formula. Mechanical advantage is equal to, that's right, the length of our effort arm divided by the length of our resistance arm. So let's plug in our numbers. 207 divided by 31, that gives us an answer of 6.68 mechanical advantage. Or we get 6.68 times the force that we apply. All right, our mechanical advantage is equal to 6.68, and it took us 3.5 kilograms to pull down one side. So let's calculate the weight of this table. So if we pulled down with 3.5 kilograms, what was the force we used to pull down? That's very good. We would multiply this by 9.8, and we would get 34.3 newtons. All right, good. Now, let's take this and say, okay, our mechanical advantage of 6.68, we only used 34.3 newtons of force. How much force are we actually lifting on the other side? Or what's the weight of the other side? So how do we find that? Very good. 6.68 times 34.3. And we get the other side is equal to 229.12 newtons. We lifted up 229.12 newtons. So now what's the weight of the table? Well, that's 229.12 newtons. So what's the mass of the table? Nice. Divide by 9.8. That's going to give us our mass. That gives us an answer of 23.38 kilograms. So in pounds, how many pounds is that? Well, to convert kilograms to pounds, you just multiply by 2.2. And we see that the table actually weighed on one side 51.436 or 51.44 pounds. Let's check our answer. Check it out, guys. We got the table sitting on the scale right here.
Actually,
Let's look.
59.
50.
It's 59. 59 pounds.
59 pounds. So pretty close. Pretty close. Yeah.
Yeah, if we were off by a couple of centimeters measuring on either side, it would make it.
So that just goes to show you. I mean, 51 to 59 pounds, 8 pounds, that's the weight of a baby, right? Or a newborn, so not changing much. There'll be a couple of problems attached to this video. Try them out.